All right, welcome to Lesson 5, Kinematic Equations. We're going to be doing example 1 in this video, but before we get too deep into the question, I want to discuss a little bit about kinematic equations because we're going to be using these a lot this year. So the first thing about these equations is we have 5 variables that we're going to be working with a lot, and those variables are velocity initial. So in some sort of problem, we want to know how fast our object is going to be starting out as. We're going to have final velocity. We're going to have a displacement, how far the object is traveling. We're going to have an acceleration. This acceleration in these kinematic problems is going to be constant. So like you're pressing on the brakes at a constant even pressure. And lastly, time. How long this takes to go through. All right. So with these equations, there are 5 of them. So we have 5 variables. Well, to solve for any of these, we need 3 out of 5 to solve for a fourth. And that's just a fact. So if we have any combination of 3 of these, we can solve for the other 2. And that is because our formulas each have 4 terms. So if we have 3 of 4, we can always solve for a fourth. All right, let's jump into the problem, and I will demonstrate this a little bit here. All right, so the problem states we're rolling a ball up an incline. So I'm going to quickly sketch a little incline for us. It's going to look something like that. And I'll toss a little ball-like object at the bottom of it and sketch a little line saying that this is going up the incline. Okay, what else do we know? It's going up the incline at a rate of 24.1 kilometers per hour. So let's write that in here right now. V, now this is its initial velocity. It's going to be slowing down as it rolls up this hill. So our initial velocity is going to be equal to 24.1 kilometers per hour. Excellent. If its maximum displacement is 9.6 meters, determine the time of the motion. All right, so here we're going to want to add in our displacement to our image. So it's going to roll probably here to here, I guess. And put that in and say our delta D for displacement is equal to 9.6 meters. Awesome. There's one hidden piece of information in here that isn't totally clear yet. So if this ball starts off rolling at 24.1 kilometers per hour, it's slowing down as it rolls up this hill. Eventually, it's going to come to a standstill. So here, this ball is going to be at rest. So our final velocity, we can say our VF is equal to 0. Cool, let's fill these terms into our chart here. So VI, 24.1 kilometers per hour. So 24.1 kilometers per hour. I want to convert that right away. I don't want to have to deal with this later. So how do we convert kilometers per hour to meters per second? Well, I'm going to do sort of the chained unit analysis that I taught you earlier. And if you're struggling with this, come talk to me and I can help you out with it. But in 1 kilometer, we have 1,000 meters per kilometer, per 1 kilometer. And we have, in 1 hour, we have 3,600 seconds. And so we're going to say that our VI, let's put it down here. VI is equal to, if we punch this in, so 24.1 times 1,000 divided by 3600 gives us 6.694 meters per second. Okay, so we have VI, and this is the value that we want to use right here. Our VF, well, that's easy. VF is 0 meters per second because it's at rest at the top. Our displacement is 9.6 meters. Acceleration, don't know. Time, don't know. Okay, well, the question is asking us to solve for time. So we want to solve for this. We want to make sure our formula has these three terms. Let me flip this around. These three terms, plus this one, and we want to exclude acceleration. We don't care about acceleration in this case. Okay, well, that step is out of the way. We have our four terms. We know that we need 3 out of 5. We have 3 out of 5. We're solving for the fourth time. Ignore acceleration. Let's choose our formula. So we want to choose a formula that has these four terms and not acceleration. If you flip through here, you will quickly find, hopefully, the formula we're looking for, and I'm going to change into a new color, is this. Delta D is equal to VI plus VF, this is in brackets, VI plus VF over 2 times T. Okay. Well, first thing we can do before we even start to rearrange this is, well, we know VF is equal to 0, so let's just substitute a 0 in there and get rid of that right away. So delta D is equal to VI over 2. And now that we don't have an addition term in here, we can just multiply this T to this term. So really we're going to have VIT over 2. In fact, I might just write it that way right now. So VI times T over 2. Excellent. Now all we have to do is isolate T and solve for it. So let's say we should multiply both sides by 2 times 2. So we're going to have 2 delta D is equal to VIT. Then we're going to divide both terms by VI. So we're going to have 2 delta D over VI is equal to T. All right, we've done it. Let's plug our numbers in and finish this problem off. I'm going to flip this T just so the formula looks like it's in a proper order here. So time is equal to 2 times our delta D, 9.6 meters, divided by VI, which we have is 6.694 meters per second. 6.694 meters per second. Awesome. This gives us a final answer of 2.9 something something seconds. But if we look back to our problem, our displacement only had 2 sig figs. So our final answer could only have 2 sig figs. I'm going to box that answer and call that done.